Okay, and I will start the introduction now. So thanks everybody for coming. Welcome to our monthly Canvas talks. These talks highlight the fantastic research that's being carried out by postdoctoral fellows in Canada and Canadian postdocs elsewhere in the world. So we know from bibliographic research by Dennis Crabtree and others that that postdocs in Canada produce a huge fraction of our published papers in Canadian astronomy, while they're precariously employed in temporary positions. So this talk series is to recognize some of that impressive work and get these names out to the community. I'm Samantha Lawler. I'm a professor at the University of Regina, which is on Canadian Treaty 4 territory, the lands of the Nahiawuk, Anishinaabeg, Dakota, Lakota, Nakota, and the homeland of the Métis-Michif Nation. Today's speaker is Dr. Alex Cridland. He completed his entire set of astronomy degrees at McMaster University on the traditional territories of the Haudenosaunee and Mississauga nations. And he's currently a postdoc at sort of a combination of Leiden and the Max Planck Institute for Extraterrestrial Physics. And today he will be talking about astrochemistry and planet formation. So thank you very much, Alex. Please take it away.
Great, thank you. Share my screen. Let's go full screen while we're at it. Yeah, so thank you, Sam. Thank you, Leo, and anyone else who has a hand in organizing these talks. As was said, my name is Alex Cridland. I'm a postdoc at the Max Planck Institute for Extraterrestrial Physics, and I spent also 3 years as a postdoc in Leiden. And I'm going to tell you a little bit about my research today, which is broadly looking at the connection between planet formation and astrochemistry, and a particular result that we found, which is what we're calling the carbon to oxygen main sequence for warm and hot Jupiters. So you've already kind of heard my bio, but just as a sort of graphical look at things, I did spend 10 years of my life in Hamilton, Ontario, at McMaster for my BSc, my MC, and my PhD. And then I shipped across the ocean to University of Leiden for 3 years, where I worked with Davina Van Dissuk in her astrochemistry group. And then I got my contract extended for a year to go work at the Max Planck Institute, which is just a short drive down from Leiden to Munich, where I am now. And so broadly speaking, what I'm interested in is to answer the question, how are planets built? Hopefully I don't have to convince anyone in the audience here why we should care the way that planets are built. But I mean, the biggest thing that we are wondering is where exactly does this diversity in the planet mass and semi-major axis really come from? And given this diversity, and practically random distribution of planets that we see in a plot like this, which is the planet mass and the semi-major axis for a number of different exoplanets, how do we actually learn anything about the underlying physics of planet formation? And then, pie in the sky dreams is to try and understand how our own solar system fits into this wider population. I mean, Jupiter itself is somewhere in this black box. So how can we really understand our own solar system? And so the way that we've done this historically, planet formation theory, is to rely on large populations of synthetic planets. So this is a system that's usually called population synthesis, the idea being that you randomly sample different variables and initial conditions that we know about from observational constraints or simulations. Compute a population of exoplanets and then compare those populations to the observations. And from that, you can actually learn a little bit about the underlying physics, say the importance of planet migration or the relative rates of your growth timescales, for example. And where my research really comes in is to try and pair this concept with astrochemistry, asking the question, where do planets actually form in their disk? And because of where they form, what is the abundance of the heavy elements, things like carbon, oxygen, nitrogen in their atmosphere? So this idea was sort of, let's say, first put forward or started by Karen Oberg in 2011, where she pointed out that effectively, if you look at the number of carbon atoms relative to the number of oxygen atoms in a protoplanetary disk, you see that to 0th order anyway, the carbon to oxygen ratio changes as a function of disk radius in your protoplanetary disk, both in the gas as well as in the grains. And these jumps that you see at these particular locations are caused by the freeze out of abundant volatiles. And these freeze outs occur at locations that we call the ice lines. So the most important ice line you should care about is the water ice line, which is around 1 to 3 AU roughly. But ice lines like the CO2 ice line, the CO ice line also have importance to the chemistry. And so you can imagine that a planet accreting, let's say somewhere out at around 11 AU outside of the CO2 ice line will have a carbon to oxygen ratio that's a lot different than a planet that accreted its gas, let's say within the water ice line, where the C to O ratio is lower. And so the goal of my work is effectively to try and combine astrochemical models for protoplanetary disks and use these models in population synthesis studies to try and compute a, let's say, chemical population for mainly hot Jupiters and warm Jupiters. And the main focus of my work for the last few years has been to look at the carbon to oxygen ratio, because that's the thing that's most easily observed in the atmospheres of giant planets. So just to define what I mean by warm and hot giant planets, they're giant, they're big, the masses are usually at least bigger than 1/10 of Jupiter mass, which is about 1/3 of Saturn's mass. The hot ones orbit their host star inwards of about 1/2 an AU, and the warm ones orbit their star between about 1/2 an AU and 10 AU, roughly speaking. So the black box that I showed you before was what I would term a warm Jupiter. And if you sort of throw down a blue box here, that you could imagine that these are your hot Jupiters. Now, about 3.3% of all stars on average have a warm Jupiter, which is about 3 times as many hot Jupiters. So it might look like the hot Jupiters are the more likely outcome of planet formation, but it's really just a detection bias in the way that we actually find planets. And if you look at the statistics of things, or other people have looked at the statistics of things, you see that warm Jupiters are quite abundant, or more abundant. For my purposes, the thing that I care about most is the fact that we can build them through planetesimal accretion models. And some of them have had their carbon to oxygen ratio already characterized. So it means that it's something we can work with. So how would you actually go ahead and calculate the chemistry of a population of planets? So there's sort of, if you can break it down into a few steps, broadly speaking, first thing you need to do is to calculate the chemical evolution of your disk. So if you're talking about the volatiles, that is the gas and the ice species, you want to use your favorite chemical kinetic code. So I use the Michigan kinetic code. I'll talk about it in a little bit. The thing that you want to add, though, is the chemical evolution of your refractories as well. This is the dust or the planetesimals in your disk. And in particular, you want to care about the carbon, because the refractory carbon component makes up about 1/2 of the total carbon in a protoplanetary disk. And there's something that's being called refractory carbon erosion, which is very important to the evolution of that carbon. And I'll talk about that as well. Once you have your chemistry all figured out, you're going to go and you're going to calculate your planet formation. And there's sort of 2 steps to this. The first being you have to build a core. If you're going to go by the bottom-up process, you have to build a core first. And then on top of that, you can accrete your gas. So I use the planetesimal formation paradigm. There's another one that's called the pebble accretion paradigm, which is also very popular. I won't talk about that today, but if you have questions, I'm happy to answer them. And then through this process, you really need to just count the number of carbon, oxygen, and nitrogen bearing species that get accreted as either gas or planetesimals onto your planet. So if we're talking chemistry, I use the chemical kinetic code from Michigan. This was popularized by Fogel et al. In 2011, but there's now a slew of papers that you can go and read about this model. For those of you who care about chemistry, these are the carbon to hydrogen, the oxygen to hydrogen, and the nitrogen to hydrogen ratios that I assume in my model. For that, it's not so important, but the thing we really want to, we don't want to jump ahead too early. The thing we want to really take a look at is the carbon to oxygen ratio and the nitrogen to oxygen ratio. We're not going to talk too much about nitrogen unless you ask me about it. And you can notice that for the volatiles anyway, the disk is quite oxygen rich on average. I assume the inheritance initial conditions, and this is basically saying that I'm assuming that everything starts as molecules to begin with. And I use a pretty typical cosmic ionization rate. And the big thing to take note here is that protoplanetary disks are inherently three-dimensional objects. If you're doing models, you usually assume axisymmetry, so that's down to 2 dimensions. But if we're talking about chemistry, I'm really only talking about the mid-plane abundances, so down to 1 dimension. Now, the refractory carbon turns out to be actually quite an important property of the protoplanetary disk. I already said that the refractory carbon makes up about half of the total carbon content. So you really need to care about how it's distributed through your disk. And what people have noticed in our own solar system, if you compare the ISM carbon to silicate ratio, and as well as the carbon to silicate ratio of objects in the outer disk, that's mostly the comets, and you compare those ratios to things that we see in the inner disk, these are the meteorites and Earth itself, you find that carbon is actually very depleted in the meteorites and Earth, which is kind of strange. I mean, presumably all of the rocks in the solar system accreted from basically the same material in the outer disk as in the inner disk. And so you would assume that the carbon to silicate ratio would be about the same, but it's not. Earth is depleted by a factor of 1,000 in carbon relative to silicon. And so you really need to care about where this carbon is actually going. I mean, if it's not in the refractories, it has to be in the gas. And if it's in the gas, then gas giants could actually go and accrete it. And this is particularly important because the refractory component, if it had the ISM carbon to silicate ratio, it would have a refractory C/O ratio of about 2. So while the gas is very oxygen rich, the volatiles anyway, the refractory component is quite carbon rich. And so the mixture of these two things becomes quite important. And so one thing I set out to do a couple of years ago was to try and have a simple model that describes the distribution of the carbon that is coming off of the grains. And so a very easy way to do this is to just derive an empirical relation for the depletion of the carbon in the refractories. So that's basically what the inset of this figure is showing you. Things outside of about 5 AU have the ISM carbon to silicate ratio, and things inwards of 1 AU where Earth is has something depleted in 1,000. And if you take this sort of depletion curve and you reverse it, then you can roughly estimate what the excess carbon would be that gets released into the gas off of the refractories. And that's what this figure is showing you here. Now, the question becomes exactly how does this carbon get released from the refractories? There's a couple of ways that you can kind of imagine. The first is, well, there's some very hot thermal event very early on in the history of the protoplanetary disk that thermalizes all the grains, releases the carbon, ablates the silicon, destroys the grains, and releases that carbon into the gas. Once it gets released into the gas, it'll start to chemically react with all of that oxygen-rich gas that I was talking about before and turn into CO quite consistently, actually. And then when the disk cools and the dust recondenses, you would form your new dust grains with basically no carbon. And you would leave these sort of carbon or purely silicate grains, let's say. And so I call this idea the reset model. And the assumption is that you release all of the carbon at t=0 for the disk. And if you're releasing it all into the disk at t=0, as the disk evolves, that gas is going to move inwards with time as the protoplanetary disk accretes material. And as a result, that excess carbon is going to move towards the host star with time. And if you use sort of typical protoplanetary disk properties, you find that after about 0.8 megayears or so, that extra carbon is gone. It's no longer available for accretion onto a planet. So that's one extreme model that you could think of. The other extreme model that you could think of is that there's some sort of ongoing chemical process that is continuously and consistently releasing carbon off of the dust grains. And there's a couple of ways that you could do that. The first is simple oxidation of the refractory carbon with OH radicals, and that would release gaseous CO very easily. The second way that you could do it is you could just take a UV photon and hit your refractory carbon head on, pop that carbon off the dust grain and have it react to form CO, of course. And while you're doing this, there's new dust grains coming into the inner disk through a process called radial drift. And so you would sort of continuously replenish this carbon-rich dust that could then be chemically processed and produce this extra carbon continuously over the whole lifetime of the disk. Until the dust from the outer disk is cut off, we won't worry about that. So whereas the reset model has this sort of evolving curve in this figure here, the ongoing model, which is sort of some ongoing process, would just be this blue curve for all time. So we have two extreme assumptions here, or two extreme models, let's say. One where we always have this excess carbon available for the accretion onto planets, and one where after a certain amount of time, the carbon disappears. And so how and when this carbon is actually released is important, because if you form your planets too slowly, then that means that by the time they're ready to accrete gas, then that extra carbon is gone. So you're going to accrete mostly this oxygen-rich gas, and you're going to end up with oxygen-rich planets. So let's combine these two things into one figure. So I showed you the Karen-Oberg C/O ratio figure before. That was assuming a static disk, but we know that disks evolve. And so this is the carbon to oxygen ratio for the gas on the left, for the solids on the right. This is just the ice for the moment. And the color shows you the C/O ratio. And in this model, you can see a couple of important things. So you still have the water freeze out at the water ice line. That's what this straight line going diagonally across the figure is. And so you have sort of low C/O ratios in the inner disk, higher C/O ratios in the outer disk. In this chemical model in particular, we had some HCN and hydrocarbon production early on in the disk life when it was still quite hot and quite dense. So that's why you have C/O ratios that actually exceed unity in these sort of intermediate disk radii. And then you get a little bit of ice or CO processing, which is when you turn gaseous CO into ice CO2, which is also an interesting process. But for the most part, you can see that the ice is always oxygen rich. The gas is mostly oxygen rich, where it has a little bit of possibility of being carbon rich, but only for a short amount of time. If we add on top of this the effects of the refractories, then you can very drastically change the distribution of C/O in your disk. And so this is using the reset model where the extra carbon disappears after a certain amount of time. And what you see is that you get a very carbon rich inner part of your disk. Even out to 5, 6 AU, you get some very high C/O ratios. And so if you could ever build a planet, especially right here near the water ice line, you could form remarkably high C/O ratios. And so we have this chemical model now. And for planet formation, I already said I used the planetesimal formation paradigm. This assumes something known as oligarchic growth, which was put forth, among others, by Kukuda and Ida in the late 90s. The gas accretion that I use is limited by effectively a cooling time scale. So it's the hotter the planet is, the longer it takes the gas to accrete onto the planet. And my planets migrate through the disk limited by something known as planet traps. And we'll talk about that in just a little bit. But broadly speaking, what you see in a figure like this is orbital radius, and this is planet mass. Similar to the observation figure that I showed you a number of slides ago, you can see that planets evolve in a fairly typical way. They evolve vertically through planet growth, whichever either gas accretion or core accretion, and they go horizontally through planet migration. And the relative speeds of these processes change with time. Planetesimal formation is very slow in the beginning. It takes quite a long time to actually build up your core. And once the core is sufficiently high, then gas accretion starts to dominate. It starts very slow, and then it goes through some practically unstable gas accretion right near the end of the formation process. Now, just a quick note about migration. The thing that I want to just get through to you is that planets go through effectively two types of migration. The first is known as type 1, and this happens for low mass planets when they're not sufficiently massive to open a gap in the disk. The torques that drive migration can be shown by this equation, which I'm just putting up there so that you can think that it's very impressive. But basically what you're seeing are two types of torques. You have the Lindblad torque, which is mostly causes the planet to move inwards towards the host star. And it's the stronger of the two torques. It tends to dominate. The second torque are known as co-rotation torques. These typically make the planet go outwards. So the two sort of fight for the overall evolution of the orbital radius of a planet. But generally speaking, the Lindblad torques win. The exception to that is at planet traps, which are discontinuities in certain properties of the disk, where, among other things, the temperature gradient becomes sufficiently large that the co-rotation torque actually becomes stronger than the Lindblad torque and reverses the direction of the migration. And so there's three important planet traps that you should care about. There's the water ice line, there's the dead zone, and the dead zone is a transition between the disk being MRI active or turbulently active and turbulently dead, we call it. And there's also the heat transition, which is a transition from the disk being primarily heated through viscous evolution to being primarily heated through radiative processes. And so what you can do is take this equation and take a typical disk model and calculate the migration for planets in this type 1. And if you do that, you get something that looks like this. This is still disk radius and planet mass, the same axes I've been showing you this entire time. But the color coding is now showing you when the planet is preferentially going outwards, which is in blue, or inwards, which is red. And the planet traps are these locations where a red is on the outside and blue is on the inside of where a planet could move. So you can imagine a planet growing up here, moving inwards with time, and then getting stuck at the water ice line, for example. But once the planet continues to grow, it becomes sufficient to break through, to break out of the trap. And at a certain point, it opens a gap in the disk and then enters the type 2 regime, which is a slower regime. So I've told you most about this planet traps because we assume that our planets are stuck in these traps for the work that I'm going to show you today. So you go put all this together, and this is generally speaking what you find. We have on the bottom panel here the evolution of the planet mass as the solid lines and the orbital radius as the dashed lines. The planets in my model start outwards of 3 to 6 AU roughly, and they move inwards with time. And then their mass, maybe not surprisingly, starts out slowly growing and then very rapidly increases. If we look at the carbon to oxygen ratio as it evolves with this time, the C/O ratio almost always starts low. And that's because the planet carbon and oxygen is mostly being determined by the ices at this point, because planetesimals are coming in and depositing ices onto the young planet. But as the planet becomes sufficiently large to start accreting its gas, then this carbon to oxygen ratio starts to go up, mostly because the gas is quite carbon rich, especially for these planets. They're all outside of the water ice line. So remember there that the carbon to oxygen ratio is intrinsically higher. And then very late stage in the formation, when the gas accretion becomes very rapid, then it locks in the final C/O ratio of wherever it may be. And here's where the choice of the ongoing or the reset model really takes hold, because the extra carbon from the ongoing model really can inflate the C/O ratio in these planets. So, I mean, this is an example of 4 planets. You'll hopefully know that any good theory paper, if you can do it 4 times, you should do it hundreds of times. And that's what I've done here. So the color coding in these figures shows you which planet trap the planet was stuck in at the beginning of its formation. And broadly speaking, the heat transition trap starts out farther away than both the ice line and the dead zone trap, with the dead zone trap usually being most inward. And what you can see is a few basic things. The first is that higher mass planets tend to have higher C/O ratios. And we'll talk about that in a little bit. There is some spread at a given mass, and the spread really is dependent on the location. So you can see that the dead zone planets and a few of the heat transition planets can have lower C/O ratios than planets forming in the ice line at a similar mass. And this is completely related to where the planet is when it's drawing down the bulk of its gas. Now, this is for the reset model, the reset carbon erosion model. If I switch to the ongoing model where the carbon is always there, then maybe not surprisingly, this entire picture sort of shifts to the right to higher C/O ratios. But apart from the shift to the right, there's not so much change between different planets. And this is the same for both the hot Jupiters and the warm Jupiters. So it doesn't seem to depend on the final orbital radius of the planet. If we put them all on the same plot, so this is now the hot Jupiters and the warm Jupiters, just to give you a better idea, as I said, you see that there's the higher mass planets tend to have larger C/O ratios. Interestingly, the ice line hot Jupiters, the hot Jupiters coming from the ice line trap, seem to be the most similar to the warm Jupiters. They sort of all lie on this same spot in this figure of C/O and final planet mass. And the hot Jupiters forming in the dead zone, on average, have lower C/O ratios than those forming in the water ice line. And this is, as I said, completely because the dead zone traps are inwards of the water ice line by the time that the planet is accreting its gas. So what about this C/O ratio mass relation? I found it very interesting. And so the goal then would be to try and understand what exactly is happening here. And what we found is something that we're calling the C/O ratio main sequence. It's basically a tight correlation between the final carbon to oxygen ratio in the atmosphere and the fraction of mass accreted as solids. So higher mass planets, on average, tend to have more of their mass coming from gas than lower mass planets. That's what I'm trying to show with this, this arrow here. For the most part, this is independent of the actual planet mass. So all of the different symbols in this figure are showing you mass bins, basically, of Neptune-like, Saturn-like, Jupiter-like, and so on. And they all seem to more or less fall along this line. This dashed line, by the way, I should have said that earlier, is the C/O ratio in the volatiles of 0.4, a ratio of 0.4. So it's clear that it's not just gas accretion going on. The solid accretion is actually quite important. And I have both populations here, both the hot Jupiters and the warm Jupiters. So this seems to be largely independent of the orbital radius as well. Now, what's super interesting about the C/O ratio main sequence is that it very naturally led us to something known as the mass-metallicity relation. So this relation is an empirically derived relation between the metallicity of a planet and its mass. And the metallicity for planet people is being defined as an element ratio, so be it the carbon to hydrogen ratio or the oxygen to hydrogen ratio relative to the solar value. So for the solar system planets, Uranus, Neptune, Saturn, Jupiter, their metallicity is being determined by the carbon to hydrogen ratio, usually determined through methane observations. And for exoplanets, it's actually done through the oxygen to hydrogen ratio, mostly through water observations, because water is actually by far the easiest thing for us to see in exoplanets. And the relation itself basically says that larger planets have lower metallicities. So not surprisingly, though, there's some scatter here. So this figure I showed you is from 2014. And then 3 years later, wait for it all comes and they find a hot Neptune that looks like it has too low of a metallicity for its mass. But let's put the population of planets that I've been showing you on a figure like this, because we can do that. So I'm showing you here the oxygen to hydrogen ratio metallicity relative to the solar value. And you can see that our population of planets, these are both the hot Jupiters and the warm Jupiters together, all sort of fall in a similar slope as the empirically derived mass metallicity relation. So it seems to be just completely caused by the C/O main sequence. You can see that there is a little bit of spread. I mean, and this spread is basically being determined by how much solids are being accreted. The more solids you accrete, the higher you tend to sit in this mass metallicity relation. There are some oddities on it. I mean, GJ436b is very metal rich for its mass, but it seems that this could be because of atmospheric evaporation. You can imagine that evaporation will preferentially remove more hydrogen to oxygen. So this will sort of artificially push up this metallicity measure. So this is looking at the chemistry of planets, but you could imagine also if you were able to go out and measure a large population of exoplanets and characterize their chemistry, you'd actually be able to learn maybe something about the underlying chemistry of protoplanetary disks as well. And so one example of this is going back to the carbon erosion that I was talking to you before. One of the parameters of this model is what I call the erosion front, what's also been called the soot line by people like Ted Bergen from Michigan. And it's basically the location where carbon begins to show its erosion. So at this point, you start to see a decrease in the carbon in your refractories. In our model, it's set to 5 AU. That's because that's what we kind of see in the solar system. Is it a coincidence that Jupiter is orbiting at 5.2 AU? Probably. So that means that we should probably explore different locations for this carbon erosion front and see how it imprints itself in the planet population. So you could imagine shifting this carbon erosion front outwards or inwards, and that would give you more excess carbon or less excess carbon as a result. So that's what we tried, and what you get is something that looks like this. So this is for the ongoing carbon erosion model. The different colored points are showing you where the carbon erosion front is in our model. And just note that for a given mass, it's the same planet. We haven't changed anything about the planet formation. The only thing that's changed is the underlying chemical model. So the blue line here is meant to sort of guide your eye to show you where a given planet shifts in its carbon to oxygen ratio, given the shift in the carbon erosion front. So maybe you can see it, but there's basically two directions to the shift. Higher mass planets seem to shift to the left if you move the erosion front to lower radii, but less massive planets seem to shift to the right for the same shift in erosion radii. And that's because the planets above this line have their carbon to oxygen ratio mostly determined through gas accretion. So if you move your carbon erosion front to the left, or, sorry, my left, I'm not sure actually, but let's say lower radii, that means that there's less carbon available in the gas in total because you've moved your carbon erosion front inwards. If you reverse that, there's then more carbon in the refractories because there's less carbon in the gas. So lower mass planets that have their carbon to oxygen ratio more determined by solid accretion shift to the right and become more carbon rich. So it's completely determined on how much gas accretion and solid accretion is setting up the C to O ratio in these planets. And so you could call planets above this line gas giants because they care more about gas, and the ones below this ice giants because they care more about solid accretion. But then Saturn at 0.3 Jupiter masses, it just gets a little confusing. So maybe we shouldn't do that. But in any case, what we've learned, hopefully, is that both hot Jupiters and warm Jupiters, the way that I've defined them anyway, seem to follow the mass-metallicity relation. It's much more related to the amount of solids that get accreted rather than where they actually end up in their formation history. This is completely driven by this main sequence of C to O ratios and the solid accretion that goes on in these planets. You do see shifts in the population that's determined by the chemical model that you assume. So better understanding the way that this carbon erosion actually occurs is crucial for understanding the carbon to oxygen ratio in planets. Yeah, that I just said. And then overall, it also is clear that you need to really care about the rate at which these solids are accreted. I mean, I'm assuming planetesimal accretion, which is a slower process than pebble accretion. But pebble accretion has a different accretion history than planetesimals do. And that is going to change the amount of solids that get accreted by the planet, which should then affect the overall carbon to oxygen ratio in those planets. So what we need then is to do both accretion models and compare those things, which is what I'd like to do in the future. But at the moment, I'll just say thank you for your attention. And if you're interested in the papers, those are the coordinates for them. And I'm very happy to take any questions that you might have.
Cool. Thank you. That was really, really excellent talk. Okay, questions. I see William Wall. Go ahead.
Hi, thanks. I have a couple questions. One, I think you may have, the first one, I think you may have answered in one way or another that wasn't entirely clear to me. Why carbon and oxygen? Why not a couple of other elements, nitrogen or whatever else?
Yeah.
Why are they so important?
Yeah, that's a great question. I mean, the simple answer is that if you look at the chemistry within hot Jupiters, especially hot Jupiters, because those are the things that we can actually characterize modulo directly imaged planets. Most of the oxygen will be in either water or CO, which have absorbing bands at wavelengths that we can actually probe. And then carbon is going to be mostly in CO. So same thing. So in terms of the easiest thing to do is to look at the carbon to oxygen ratio. That's not to say that it's easy. It's actually very difficult to infer the C/O ratio in atmospheres. But if you talk about nitrogen, most of the nitrogen wants to be in molecular nitrogen, N2, especially at hot temperatures and temperatures and densities in hot Jupiters. And that's invisible, effectively. It has no dipole and a very weak quadrupole moment. So we cannot look for N2, basically. You might be able to find ammonia with JWST. You should be able to find HCN also with JWST, but their abundances are going to be quite low compared to what they would be in N2. Yeah. Now sulfur is another story. It might be also observable with JWST. And the chemistry underlying sulfur is still very new. So it hasn't really no one's really picked it up yet. Or there have been a few papers, but not too much. But sulfur is the next thing. So it'll be carbon, oxygen, nitrogen, and sulfur are probably the four big ones.
Okay, great. My second question is, it's somewhat whimsical, I suppose. Imagine you have astronomers looking back at the early solar system as it's forming. It has its disk with its gaps and its particular chemistry and so on. So they can take images of our proto solar system over time, maybe over periods of billions of years. With the observations we now have and with models that you're talking about, can we actually create simulated images of our solar system at different stages in its evolution?
Oh, that's a great question. I mean, you could make simulated images. I guess whether they are accurate or not is another question. So yeah, yeah, that's a great question. So we've started to be able to detect accreting planets in protoplanetary disks at an age of about 5 megayears. So PDS 70 is, and its 2 planets is the prime example. But those are very massive planets. There are about 5 Jupiter masses, roughly. And they're accreting quite a bit of material still. So, and they're also at fairly large radii. So with our current technology, I would say we wouldn't be able to see our proto solar system the way it was. But yeah, I mean, give technology enough time, and yeah, you'll start to get the angular resolution needed to image a proto solar system. for sure.
Yeah, that's sort of going beyond my question. My question was just create a simulated image first, and then I'd ask a question about what would our technology allow us to see such a thing. So you sort of anticipated my next.
Yeah.
Yeah.
I mean, we can make so there is a model to describe where Jupiter was throughout its history. I mean, the Grand Tack model is very popular, and the Nice model is also like this sort of next step after the Grand Tack model. So we do have a sense of where Jupiter was at sort of while it was forming. So yeah, in principle, you could go and make an image of that for sure.
Right. Thanks.
Yeah, no problem. It's a good question.
Other questions? Arnaud?
Hi, hi, Alex. Thank you very much for the great talk. I had a quick question, and maybe I missed it. It was a detail, but I was curious to hear a bit about your thoughts about timescales. Because I on some of the plots, it seemed like everything was going really fast. Within just over 1 million years, you were done. So I was curious to hear your thoughts and how do those impact some of these results, like varying the timescales?
Yeah, so I mean, let's go back to. So I mean, for me, the most important timescales if you're talking about chemistry, then the most important timescale is, I mean, if you're going to talk about the carbon erosion story, then yeah, you really need planet formation to happen quickly if you want to get extra carbon in your planet. So part of the motivation for developing this was that, around 2017, 2018, there were some observational works that was suggesting that most hot Jupiters are more carbon rich than their stars. And that seems very difficult to do from a theoretical point of view, because the volatiles are all oxygen rich, the ices tend to be oxygen rich. And so you needed a way of getting extra carbon. And that's where we sort of got this idea of carbon refractory, because it is half of the carbon basically. And then if you can release it into the gas, then it's more easily accreted by a giant planet. But indeed, I mean, a lot of my planet formation is happening within about a mega year from when I started. And yeah, my disk models are sort of meant to represent at t = 0. They're sort of meant to represent the transition from the class 1 disk to the class 2 disk, that sort of transition time. It's really difficult actually to say exactly when t = 0 is. Yeah, I mean, but yeah, it does happen quickly. I will admit that.
And I guess as a follow-up, if you were, because I guess when you're looking at your disk lifetime, essentially, what's the ballpark you're working with, and if you were to increase that, and so allowing this like class 2 phase to be stretched out, and maybe a slightly longer class 1 phase, does that make it easier in some sense to resolve a bit this conundrum of like bringing in all this carbon? Or
yeah, so it's a good question, because we're not really sure. I mean, first off, we're not really sure how the refractory carbon is getting released from the dust. I mean, this is ongoing work from many groups around the world working on this. So if it is this sort of reset scenario that I discussed, then it is going to happen at some point in the class 1 phase. And so, yeah, to what radial extent this excess can actually happen. So let's say instead of 5 AU, it's over 15 AU. Now the excess carbon can last longer because it's going to advect. It takes longer for it to advect into the host star. And actually, yeah, we didn't even really play with that. We should have played with that a little bit more, about moving it outwards and seeing what happens, or like very far out. Indeed, but there is still this question as well about when you actually make your planetesimals, and that's a completely other, problem, because yeah, it's not exactly clear when exactly that should happen. if it is early, then that helps planetesimal formation models, because it gives us more time to build planets, which is nice.
Yeah, for sure. Cool. Thank you very much.
That
Yeah. I guess
roughly answers the question.
Yeah. I'm also, I guess, curious if for example, you say that your class 1 phase duration doubles and you double your class 2 lifetime, like disk lifetime. Then can you have that like bigger radial extent? Like, does that make it easier to a great extent? That's, I think, the main like motivating question.
Yeah, I mean, the class 1, extending the class 1 phase would be interesting. I will say extending the class 2 phase is, from a planet from our model standpoint, the model that I'm showing here anyway, it's not as important because we put a fairly stingent end to our planet formation. I mean, you can see that the planets grow up very quickly and then they just stop forming. And that's probably not realistic. There's probably sort of a tail end of planet formation where the planet is still sort of sipping on the gas. Yeah. So in that case, then it does matter how long your disk lasts for. But for our models, it's less important. Yeah.
Okay, sweet. Thank you.
Yeah, thanks.
Any other questions from the audience? I have a question then. Is our JWST measurements going to like totally be awesome for testing these models, or not really? You mentioned it briefly, but what do you think?
So I think in terms of getting better estimates of the C/O ratios that we know now, or that we've measured now, it's going to be better because the sensitivity is higher. The trouble for my work is that I would really like to see a large population of planets characterized, which is asking a lot of JWST, because there's lots of people, probably people in the audience, that are asking for time that aren't going to point it at planets, even though they should. And so for me, so JWST, the nice thing is that they are going to point it at different massed planets. So there's going to be sub-Neptunes, I think a couple of super Earths, and then they're going to do the hot Jupiters again, and maybe a warm Jupiter, like one on the edge. So at least they're going to get a mass range that I can work with, which is nice. What I'm really excited about is the ARIEL mission, which is a new medium mission from the European Space Agency. And they're set up to do between 500 and 1,000 exoplanet chemical characterizations in the near and mid, in the near infrared, up to about 8 micron, I think. And that's when you're really going to start to see these populations grow and really start to get a sense of how things look. It's kind of like, it's going to kind of be how Kepler was for planet detection. It's going to be the same sort of idea, but for chemistry in the atmospheres. So, and that's supposed to launch in 2026, I think. So JWST is going to do a ton for being more confident about these C/O ratio measurements, but it's going to take like a really big survey, I think, to really start to learn a lot about planet formation. Yeah.
Cool. Thanks. Any final questions? I think we've got time for like one more. Anybody has anything? Nope. If not, thank you very much, Alex. That was fantastic. Thank you for staying up so late to talk to all of us in Canada. And next month we have Nicole Dracos at University of Santa Cruz, who will be talking about dark matter halo computational stuff. So so please join us next month. Thanks, everybody.
Awesome. Thank you very much.
Thank you.